In 1976, NASA sent two spacecraft to the surface of Mars. They were humanity's first experiments specifically designed to detect living, breathing extraterrestrial microbes. When Viking 1 touched down in the Planitia region, the early data suggested an immediate success. The instruments were functioning perfectly, ready to scoop up the red dirt and test it for biological activity. This diagram shows the mechanics of the labeled release experiment. Robotic arms fed the soil a liquid nutrient laced with radioactive carbon. If microbes were present, they would consume the nutrient and exhale radioactive carbon dioxide. Within hours, the instrument registered a massive spike in radioactive gas. To verify the result, the team ran a biological control test by heating a second soil sample to 160 degrees Celsius. This sterilization process stopped the gas release entirely, producing a flat line that perfectly met the mission's predefined criteria for life. By the mission's own pre-flight criteria, Viking had successfully detected extraterrestrial life. This conclusion stood for only a few weeks before being systematically dismantled. The rejection came from a second instrument on the lander, the Gas Chromatographer Mass Spectrometer, or GCMS. Its job was to find the physical organic molecules, the bodies, required to confirm the first experiment's results. The methodology of the GCMS was aggressive. To vaporize and identify organic material, it baked the Martian soil to an extreme 630 degrees Celsius. But the results were negative. The GCMS found no complex organics, only trace amounts of chloromethane. NASA scientists concluded this was Earth-based contamination, likely leftover cleaning solvents from the cleanroom where the craft was assembled. The scientific community moved quickly to a new consensus. No bodies, no life. The positive metabolic results were written off as an unexplained chemical reaction in the Martian dirt. A single negative reading from the GCMS successfully overrode the positive detection of life. The book on Martian biology was closed, and the planet was characterized as a sterile desert for the next 30 years. This consensus remained unchallenged until 2008, when the Phoenix lander discovered high concentrations of perchlorate, a highly reactive chemical salt, in the Martian soil. For a minority of researchers, this discovery reopens the Viking case. It suggests the design of the GCMS oven had a critical oversight. It ignored the soil's own chemistry. Heating Martian soil containing organics and perchlorate to 630 degrees Celsius triggers a microscopic detonation. The reactive salts incinerate organic molecules before sensors detect them, leaving behind a specific byproduct, chloromethane. This is the exact chemical Viking dismissed as cleaning solvent in 1976. If the instrument designed to confirm life accidentally incinerated the evidence, it means the original positive detection from the metabolic experiment could be entirely real. However, the broader scientific community points to a different conclusion. Perchlorate also provides a non-biological explanation for the original positive life detection. Cosmic radiation breaks perchlorate down into hypochlorate. Mixing this chemical with the 1976 liquid nutrients triggers an abiotic gas release, mimicking a living metabolism. Because heating the soil destroys hypochlorate, this simple chemical reaction perfectly reproduces the flat line seen in Viking's biological control test. If microbes truly exist in that soil, it raises the question of their origin. Theories of lithopanspermia suggest that life could have hitchhiked between Earth and Mars on debris launched into space by ancient asteroid impacts. We are left in a scientific deadlock. A single chemical salt can explain both how an instrument could fake a biological signature and how another could destroy it. To solve the mystery, the obvious next step is to send a modernized, better calibrated oven to Mars and rerun the 1976 tests. But we now know the Martian surface environment actively destroys the evidence. Recently, the Perseverance rover carried a target made of 100% organic material to the surface for a 1,000-sol exposure test. This chart shows the degradation. Intense UV radiation shredded the organic signal by a factor of 5 in just 500 sols. The surface of Mars acts as a hostile witness, erasing its own molecular history. This makes simple topsoil testing with ovens inherently unreliable for finding ancient remains. Modern exploration has shifted focus. Rovers like Perseverance now drill into ancient river deltas, seeking complex carbon locked deep within protective mudstones where it is shielded from radiation. But the standard of proof remains high. Scientists recognize that these organics can form through geological processes or meteorite impacts, and no longer assume a biological origin. Final resolution for the Viking case will likely require the Mars Sample Return mission. For the first time, pristine rocks will be analyzed in Earth's most advanced laboratories, away from the limitations of robotic ovens. We still don't know if NASA accidentally discovered life in 1976. The mission's true discovery was how chemically deceptive a planet can be. Viking left behind a difficult legacy. In the search for life beyond Earth, the initial discovery is only the beginning. The real challenge is surviving the burden of proof. The surface of Mars is cold, irradiated, and utterly silent. Yet in 1976, Viking landers arrived here to ask if it was hiding something alive. What they found instead was a mystery that questioned the reliability of chemical detection. The telemetry from the two landers told two different stories. The labeled release experiment detected a signal of active biological metabolism in the soil, but the onboard mass spectrometer, searching for the organic carbon molecules required for life, found zero. It took over 30 years for the Phoenix lander to solve the puzzle. The Martian soil wasn't teeming with microbes, it was saturated with perchlorate, a highly oxidized salt. When the Viking instruments heated the soil, those perchlorates acted like a powerful bleach. They destroyed organic compounds and released a gas that perfectly mimicked biological respiration. The regolith itself was producing a false positive. Simple chemical reactions on a lifeless world were flawlessly imitating the metabolic breath of living organisms. This created a new standard for astrobiology. If basic chemistry can fake a metabolism, chemical tests alone are insufficient. To definitively prove life exists, researchers realized they needed a structural, physical signature that lifeless chemistry could never forge. In 1984, researchers on an Antarctic ice field found a 4-pound chunk of rock. Isotope analysis confirmed it was a piece of ancient Martian crust, blasted off the planet millions of years ago and preserved in the ice. 12 years later, a team cracked the meteorite open and placed it under an electron microscope. Embedded in the rock were tiny, worm-like structures that resembled fossilized nanobacteria. Deep within the rock's carbonate globules, scientists identified unusual, rectangular crystals of a mineral called magnetite. On Earth, magnetite crystals with this specific, elongated, prismatic shape are produced exclusively by magnetotactic bacteria, which use them to navigate magnetic fields. Right alongside these crystals, researchers detected polycyclic aromatic hydrocarbons, complex organic molecules. The organics, minerals, and physical shapes were all locked together in the same microscopic regions. The combination of bacterial shapes, rare mineral prisms, and trapped organics presented a compelling case. For a moment, science found the undeniable footprint of Martian life. The claim of extraterrestrial life requires that any lifeless geological process be ruled out first. Researchers had to determine if these microscopic patterns could be explained by geology alone. High-resolution transmission electron microscopy eventually revealed that an abiotic imposter was responsible. During an ancient, violent meteor impact, extreme shock heating caused the iron-rich carbonate within the rock to completely and thermally decompose. These panels show the results of that shock heating. The process triggered solid-state diffusion, which spontaneously formed these rectangular magnetite crystals without biological intervention. These inorganic crystals flawlessly mimicked the exact geometry and lattice alignment of biological magnetites. Even the associated organic molecules turned out to be common in lifeless asteroids and deep space. The Allen Hills meteorite provided a harsh lesson. Physical morphology, things simply looking like life, cannot be used as unambiguous proof of biology. A new requirement emerged from this debate. A potential biosignature is only valid if it possesses undeniable geological context. Researchers now use 3 strict requirements: an ancient habitable environment, the chemical ingredients for life, and a geological mechanism for long-term preservation. The center is the only place astrobiologists can safely separate complex chemistry from a true biological fossil. Isolated findings are no longer accepted. The surrounding planetary environment must corroborate the biological claim. This is why the Perseverance mission is focused on Jezero Crater. This dried-up ancient lakebed was selected specifically to provide that necessary geological context. At the Bright Angel outcrop, Perseverance reached a mudstone nicknamed Chiava Falls. Inside the rock, the rover detected macromolecular carbon, the complex structural foundation of life, locked alongside phosphate and iron sulfide minerals. Close-up imaging revealed millimeter-scale leopard spots. These resemble terrestrial redox reaction fronts, which microbes use to harvest energy. NASA remains cautious because these same mineral associations could be forged abiotically by sustained high temperatures or highly acidic fluids. Despite finding the most compelling potential biosignature to date, the rover's remote instruments cannot definitively rule out lifeless chemistry. A 1,000 sol aging experiment conducted by Perseverance on an organic target from Earth highlights the difficulty of remote detection. Intense radiation at the Martian surface degrades organics over time, altering their chemical signatures and limiting what the rover's instruments can see. The only way to bypass these illusions is to bring the samples home. Bringing these sealed titanium tubes back to Earth's state-of-the-art laboratories is necessary for a definitive conclusion. If life did exist on Mars, it raises the possibility of lithopanspermia, the idea that microorganisms can be transported inside meteorites between planets. Confirming a biological origin in these returned rocks would suggest that life did not start on Earth in isolation, but instead migrated across the inner solar system.